All right, today we are diving deep into the very heart of how artificial intelligence works. We're going to look at the fundamental components, the real nuts and bolts, the layers inside a neural network. Let's get right into it.
So, you ever just stop and wonder, how does an AI go from a bunch of jumbled pixels in a photo to saying with total confidence, yep, that's a cat? How does it actually, you know, think? Well, I promise you, it's not magic. It's all about the structure, and that structure is built piece by piece using things called layers. Here's the game plan for this explainer. We'll start with the basic building blocks, then dissect the anatomy of a simple network. After that, we'll explore how that network actually thinks, see how a simple diagram turns into real code, and then we'll wrap it all up with the key takeaways. Okay, let's kick things off with the absolute basics, the building blocks of AI. To get anywhere, we've got to answer one simple question first. What in the world is a layer?
In the simplest terms, a layer is just a group of artificial neurons that are all working together on the same team. Think of them like a row of tiny, specialized calculators, all crunching numbers on one part of a problem before passing their answers to the next row of calculators in line. Now, here's the thing. Not all layers are created equal. They come in different flavors, each one specialized for a particular job. You've got your dense layers, which are kind of the all-purpose workhorses. Then you have convolutional layers, which are absolute wizards when it comes to images. They're fantastic at spotting things like edges, textures, and shapes. And recurrent layers? They're designed for sequences, like words in a sentence, or maybe stock prices over time. Each one is a specific tool for a specific task. So, we know these networks are made of layers. But how do they all connect? How do they fit together? Let's take a look at the anatomy of a really simple network to see how it all clicks. At its core, even a basic neural network has three main sections. First, you've got the input layer. This is the front door, right? It's where your raw data, like the pixels from an image, first enters the system. Then you have the hidden layers. This is the engine room where all the really complex, heavy-duty calculations happen. And finally, you have the output layer, which spits out the final answer, the prediction, like cat, dog, or whatever you're looking for. And speaking of that output layer, its size is absolutely crucial. Let's say you're trying to classify a picture as either a cat or a dog. Well, you'd probably have two neurons in your output layer. But what if you wanted to add a third option, like a lizard? Well, just like we're showing here with the number 3, you would just add a third neuron to that output layer. It's a direct one-to-one match. The number of possible answers you want determines the number of neurons in the final layer. Okay, this is where it gets really, really cool. We get the structure now, but how does the information actually move through these layers? How does it get processed? Let's get into the mechanics of how a network actually thinks. So, every single connection between neurons has something called a weight. The easiest way to think about a weight is like a volume knob on a stereo. It controls the strength or the importance of that connection. A really high weight means the signal coming through is considered super important for the final prediction. A low weight means, not so much. Now, after a neuron adds up all those signals coming in, it doesn't just pass the raw number along. No, it runs that number through an activation function. This thing acts like a mathematical gatekeeper. It takes the total input and squashes it, usually into a clean value between 0 and 1. This basically decides how fired up or activated that neuron should be before it sends its own signal to the next layer. So this is the 4-step dance for every single neuron. It receives inputs from the previous layer. It computes a weighted sum, multiplying each input by its weight. It applies that activation function to make a decision, and then it passes its final output to the next layer. This exact process happens thousands or even millions of times, all at once across the entire network. It's a massive coordinated effort. And this right here, this is the secret sauce. This is how the AI actually learns. The network isn't static. As it sees more and more examples, it's constantly tweaking and adjusting all of those little weight dials on its own. It's trying to find the perfect combination of settings that leads to the right answer. That process of continuous adjustment is learning. Okay, understanding the diagram is one thing, but what does this look like when the rubber meets the road? Let's see how this abstract idea of a network gets translated into actual real-world code using a popular framework called Keras. So check this out. On the left, you've got our simple network diagram. 3 inputs, 5 hidden neurons, 2 outputs. And on the right, believe it or not, that's the entire network written in code. It's a direct one-to-one translation. It's kind of amazing, right? Let's look a little closer. Look at this very first line here, dense 5. That's just us saying, hey, create our hidden layer with 5 neurons. Pretty straightforward. But look at that input shape equals 3 part. This is the really clever bit. That tells the model what to expect from the data coming in, that the input layer will have 3 features. So with one line, we've basically defined both the input and the first hidden layer.
And the next line is even simpler. It just says dense 2. This creates our output layer with 2 neurons. See how we don't have to tell it where to get its inputs from? The model is smart enough to figure that out on its own. It knows the last layer had 5 neurons, so it just automatically connects everything up.
And that is it. Seriously, let that sink in. The entire structure we've been drawing and talking about, the inputs, the hidden layer, the outputs, all the connections, is captured in just these few lines of code. It just goes to show how incredibly powerful and efficient these modern tools have become.
Okay, we've gone all the way from abstract concepts to actual lines of code. So let's zoom out and quickly recap the most important things to remember from all this.
So, what did we learn? Well, first, that neural networks are built from these layers of neurons and that you use different types of layers for different jobs. We also learned that the real thinking and learning happens as the network adjusts its weights and fires its activation functions. And maybe most importantly, we saw that this complex idea can be turned into just a few lines of code, which lets you stack these layers up to build bigger and more powerful models.
So in the end, that's what layers are. They're the fundamental building blocks of AI. They're the Lego bricks that we can snap together to build everything from a simple image classifier all the way up to the massive, complex models that are generating art and writing stories today. So now that you understand the blocks, the only real question left is, what are you going to build?